Hey everyone, in this part of my gas leak detection project, let's talk about how we bridge my assembly code with the Arduino IDE using a simple but powerful INO file. First, I declare an external C function called start. This tells the Arduino compiler that start is defined elsewhere, specifically in our AVR assembly file. The extern C block ensures there's no C++ name mangling, so the linker can match it correctly. In setup, I immediately call the start function. This effectively hands over control to my assembly code. From here, my low-level program takes full control, initializing registers, timers, and starting the loop logic I defined in assembly. And finally, the loop function is intentionally left empty. That's because your infinite logic loop isn't handled by Arduino's usual runtime, it's handled entirely in assembly. Once start is called, my Arduino behaves like a pure AVR machine. This, I know, is essentially just a launcher. It uses the familiar Arduino environment to upload my assembly logic, making it easier to combine low-level control with the Arduino toolchain. Super efficient and super powerful. In this part of the video, I'll walk you through the AVR assembly code I created and explain exactly how it works and why I implemented it this way. I start by defining bit masks for each pin. This makes the code easier to read later on. Each component, like the buzzer, fan, servo, LEDs, buttons, and gas sensor, is tied to specific ports on the microcontroller. I declare a variable in SRAM called state_on. This holds the on OFF state of the system and acts as a simple memory flag. The start label is called from the INO file using extern C. From there, I jump straight into main, where I initialize the stack pointer, critical for memory operations, especially in assembly. Section 3, IDE configuration. I set port B pins as outputs, buzzer, fan, and servo. Then I configure the red and blue LEDs as outputs. Here I make PD5 and PD for inputs for the on and OFF buttons, and one enable internal pull-up resistors, so the buttons default to high unless pressed. I also configure PCO, the gas sensor input, as an input pin. Section 4, TIMER1 setup for Servo PWM. I enable Fast PWM mode for timer 1. This is important for driving the servo motor precisely. I set the top value for the PWM to 4999, giving us a 20 milliseconds pulse, period, standard for hobby servos. This sets the servo to its default position, 0 degrees, which corresponds to a 1 millisecond pulse. Section 5, main loop and button checks. Every loop iteration checks if either on or OFF button is pressed. These bits are checked using SBRS. If the button is low pressed, we jump to toggle the system state. Section 6, button logic. This waits for the on button to be released, helping to prevent bouncing. When released, the system state is set to on. Same logic applies for turning the system OFF. Section 7, GAS sensor check. I check if the system is on. If so, I move on to read the gas sensor. If gas is detected low signal from MQ-2, I jump to gas_detected. Section 8, no gas logic. I turn on the buzzer, fan, and red LED, and turn OFF the blue LED, indicating safe status. Servo stays at 0 since everything is safe. Section 9, gas detected logic. Now, when gas is detected, I reverse the signals. Buzzer and fan OFF, red LED OFF, blue LED on, indicating alert status. I move the servo to 180, simulating a valve closing or a cover activating. Why I did it this way? This code is built for speed, direct control, and reliability. It doesn't depend on libraries. It gives me complete hardware control for a safety-critical project. Everything from button debouncing to PWM timing is optimized to make sure the gas leak system responds immediately and predictably. Justification for code implementation: AVR assembly gas leak detector. 1. Efficiency and full control, assembly language. I chose AVR assembly because it gives full control over the microcontroller, every clock cycle, every pin, every register. It's not just about getting the project to work, it's about understanding what makes it work. 2. Direct hardware manipulation. I implemented SPI, CBI, in and out instructions because they directly control the hardware pins without the overhead of digital write or pin mode. This means faster reaction to sensor input and actuator control, important when you're dealing with potentially dangerous gas leaks. Rather than using libraries, I set up Fast PWM using Timer 1 manually. This lets the servo rotate smoothly from 0 to 180, which is critical for mechanical actions like opening or closing a valve. By setting ICR1 and OCR1 values myself, I fine-tuned the servo angle precisely. 4. Clean button handling with debounce logic. I used SBRS and SBRC with loops to wait for button release. That's intentional. It avoids bouncing and ensures the system doesn't toggle multiple times with one press. It's a clean and stable way to handle physical inputs. 5. Memory efficient state tracking. I used a state underscore on flag stored in SRAM via STS and LDS. This allows me to track whether the system is armed without needing global variables or redundant checks. This approach keeps the system flexible and minimizes memory usage. 6. Assembly plus Arduino equals best of both worlds. The INO file simply calls start from assembly, nothing more. It uses Arduino's loader for convenience, but the logic is 100% hand-built. It's a hybrid approach, the ease of Arduino uploads, with the speed and precision of pure AVR assembly. This wasn't just a coding exercise, it was an exercise in precision, optimization, and learning how machines actually operate. That's why I implemented the code this way. Every line was written with purpose. This line says, "Hey R16, take this exact value, no memory read, no calculations." Imagine grabbing a saved setting from RAM and placing it into your hand. That's what LDS does. This saves whatever is in R16 into a memory location, like setting a timer register. Think of this as asking, "Hey, is R19 equal to 1? It sets flags based on the result. This acts like a loop or a shortcut. Go back to that spot up there and repeat. It's like saying, if this button isn't pressed, just move on to the next check. It's perfect for handling buttons or sensors that go HIGH. This brings the state of input pins into a register, for example, to check if a button is pressed. I use this to configure pins, like setting port B as outputs. It's part of setting up memory for function calls or interrupts. Without this, the stack won't work properly. I use this to turn on certain bits without affecting others, often for enabling pull-up resistors. This is used to turn OFF, specific bits like configuring certain pins as inputs. And that's the full breakdown of the AVR assembly gas detection project. You found this explanation helpful or want to see more real-time embedded projects like this? Don't forget to like, subscribe, and comment below. Thanks for watching.